So, good day, everyone. My name is Carlotta Berry. I'm a professor of electrical and computer engineering and robotics at Rose-Hulman Institute of Technology in Terre Haute, Indiana. And I am also a Noir STEMinist. My research focuses on robotics education, human robot interaction, open source robotics, which I do with 3D modular robots called the Lilybot, where we add and 3D print parts so that the robot grows with the user by using things like a microbit, Raspberry Pi, Circuit Playground Express, ESP32, and more. And I am so excited to be today's MC for our Motorized Movement with Hackster.io Impact Spotlight. And I would like to now get ready to introduce our first awesome video for today. It is from OmniFetch, and it is a hazardous material handling and teleoperated industrial delivery circuit. It is great for being inclusive and to keep people safe if they have to teleoperate and move hazardous materials around. I hope you enjoy.
Hi, thanks for joining us for today's Impact Spotlights hosted by Hackster. My name is Dominic Lee, and it's my pleasure and honor to share with you our award-winning project, OmniFetch. So OmniFetch is essentially our award-winning hackathon project. It is a hands-free gesture-controlled robotic assistant for hazardous material handling and teleoperated industrial delivery. This project was built as part of a 36-hour hackathon hosted by Seed Studio, Hackster.io, and NVIDIA. And of course, right here is my team. Together, we are a group of passionate engineers at Circuit Launch. We're also mentors. On the right side, we have a photo of our innovation here, and we're demonstrating it to a group of audience members and judges. Now, with that said, let me tell you a little bit more about myself. So, as you know, I'm an avid inventor, programmer, designer, and engineer. And I run a tech startup in California that provides a patented wearable technology which enables users to seamlessly control electronics, computers, robotics, and more with the flick of the wrist. And this patented award-winning technology enables users not just to control robots, but to feel empowered and control them from a safer distance. Now, aside from that, I'm also a roboticist in residence at Circuit Launch. Circuit Launch is an innovation hub that provides labs and facilities for robotics companies and startups. So as a roboticist in residence, I've helped various clients realize their dream use cases, especially when it comes to robotics, wearables, CAD design, and IoT-based platforms. Additionally, I'm also an honored alumnus from Purdue University, and I used to be the former club president of Purdue Mechatronics Club. It's always my passion to be able to help and lead where I can. In collaboration with Purdue University, one of my projects, the Gyropump Vimpact Framework, which controls robotics, enabling them to be controlled by AR glasses and our one and only Gyropump technology, has been featured and supported by the National Science Foundation. And some of my other works, such as the Lightbeam Flight Simulator, various workshops that I've led, as well as my discussion, my talk at Circuit Launch about AI and robotics. These are some key highlights that I'd like to share about just things that I've done for the community and things that I passionately would continue doing as part of just exploring what's possible in the realm of innovation, robotics, and automation. Now, another thing that I'd like to share, which inspired me to build the project behind OmniFetch, is our Gyropalm Spectrum product. It is actually something that's available on the market today, and it comprises of market-leading Vuzix AR glasses along with a Gyropalm wearable, all enclosed in the waterproof case. Now, this product is able to drive different robots. As you can see here, we have it driving the Boston Dynamics Spot. One of our colleagues has the Boston Dynamics Spot, and we're able to drive it from a far distance. And you can see on the corner of your eye, you'd be able to visualize the operator's view, see what the robot sees, and just explore remote areas without actually being there. So this is a very powerful tool, and it actually won the most promising innovation of the year at Sensors Expo. For those of you who don't know, Sensors Expo is North America's largest electronics design event for engineers. And so it's also an honor for them to feature me on their front page as well. Now, let's talk about the innovation at hand. So the OmniFetch. OmniFetch is a hands-free robotic object transport mechanism. So what this means is, well, most AMRs, or autonomous mobile robots, they're large and they're not able to grab objects on shelves. They're not able to move things efficiently. And typically a mobile robot has what we call a docking variance of up to 2 to 4 inches. That means without AI and without robotic arms, it's very difficult for an AMR robot to carry things. And what we've done is we've added intelligent robot arms, right? The Lee robot arms. And we've been able to drive this robot along with those arms using cutting edge AI technology. All right, with that said, we can share with you a little bit more about putting together the pieces and how we built this during the hackathon. To even begin with, we needed preparation for the hackathon beforehand. So we obviously had the Omnibot V2, the V2 AMR here, and we also have the Seed Studio Recomputer Mini, which was lent to us during the hackathon, and as well as the Seed Studio Lee Robot Arm 100. So these were things that we have mounted on the robot and prepared. In addition to that, we also have the Gyrapalm Developer Kit. This is the official Gyrapalm DK2, and it includes the wearable receiver base and so forth. And this allows us to drive the robot and train it for SLAM mapping and navigation. And of course, you can't do simultaneous localization mapping without the LiDAR, right? So we have the SlamTech S2L LiDAR, and we also have a custom wooden base, which I've CNC'd beforehand. This is something that fits right on top of the robot and allows it to mount various robotic arms and carry different payloads. Now, we also have 2 of these USB cameras. So basically, these 2 cameras are mounted on top of each Lee robot so that you have a clear view of what's being displayed here. And you can use that as training data for the algorithms and for training the model, essentially. We also have plastic trays and objects, and this is obviously the items that are being experimented with. Now, the Lee robot arm offers impressive precision, but to achieve that, we had to build this into the calibration sequence and to have to modify the servos in a way that enables it to pick up objects efficiently. So as you can see here, we use plastic bins so you could distinguish where objects are placed. Also, my team and I performed this during a 36-hour hackathon. So we had the pleasure of meeting with some leaders from NVIDIA who were very impressed with our innovation, as well as a quick shout out to Alex, the CEO of Circuit Launch. Now, our ACT model was trained using collective motion data to predict the arm trajectories, right? This would enable the robot to go to the predicted object locations, even if these are displaced or misaligned. And we wanted to adapt to various situations. So that means in different lighting conditions, we need to ensure the robot refines its skills. And so we had to train about 20 to 40 samples to begin with, and we scaled it up from there. As for the training, we trained it with a model, the ACT model initially, which is the action chunking transformer that enables it to record different episodes and play them back. Now, in the future, obviously, we will improve the stability with a hybrid mixture of models that have more grounding to it. The current model, though, is very reliable for the most part, and it's able to drive to different places and pick up objects. With that said, let me actually show you the video that we've presented, and this will give you a better idea of the demonstration.
Introducing Project OmniFetch, a hands-free gesture-controlled robot assistant for hazardous material handling. This project leverages cutting-edge technologies to create a hands-free, remotely operated robot assistant capable of picking up and transporting critical or hazardous objects in unpredictable environments. By combining gyropalm gesture control, intelligent object manipulation, and dynamic teleoperation, we've created a solution that tackles latency issues common in remote control systems, while improving accessibility for those with disabilities or reduced mobility. Our project integrates a Lee Robot open-source robotic arm mounted on an Omnibot V2 mobile-based platform. Our solution has the ability to dynamically pick up objects, even if displaced or rotated, making it an ideal solution for handling hazardous materials, assisting disabled users with medication retrieval, or serving as a tabletop butler in busy work environments. Prior training is performed by the end user on various objects to demonstrate proper robotic gripping behavior. After dozens of samples, training was initiated on an NVIDIA-powered GPU computer running CUDA. Using the ACT, or Action Chunking Transformer policy, we are able to have the gripper dynamically locate objects at the closest table or workbench surface and move them onto the robot for further transportation to a designated waypoint. The Omnibot then autonomously drives to the designated location, or optionally can be driven by a human operator using gestures with the GyroPalm Encore wearable. We hope our project inspires further advancements in accessible robotics, leveraging hands-free control and adaptive learning to create smarter, more responsive machines that empower human operators while accurately accommodating for imperfections in the robotic control paradigm.
All right. As you can see, this robot is very effective, and it's become a proven project that showcases intuitive and reliable object handling using AI and gesture control. So we're currently in close works with Purdue and some industry leaders to bring this technology to more labs and facilities. And this robot can be flexibly upgraded with better robotic arms in long term. With that said, we appreciate you for your time. If you're interested, feel free to visit our Hackster.io project page, as well as our profiles, and feel free to give us a like on social media and follow us for more details. If you're interested in an Omnibot V2 AMR for your facility or lab, or buying some GyroPalm Spectrum kits, feel free to reach out to me directly at dlee@gyropalm.com. Thanks for watching.
Wasn't that absolutely amazing? Thank you so much, OmniFetch and Dominic Lee, for sharing your project with us today. And now we will keep on going with all of the great impact spotlights. Next up is going to be Braden Sunwald, or better known as Bare Naked Embedded on most social media, with a DIY electric kayak. He's an electrical engineering student from Seattle, and this project is about integrating AI and machine learning into one of his loves, which is kayaking. Sit back and enjoy.
All right, welcome to the Impact Spotlights, July 31st. Thanks, Hackster, for the invite. So this talk is called Putting AI Inside a Kayak, DIY Electric Kayak. My name is Braden Sunwald, but most of my handles online, I go by Bare Naked Embedded. So a little bit about me. I got my BA in electrical engineering in 2019. And I've been working as a firmware engineer for about 4 or 5 years now. And I've been working on UUVs, so basically think underwater drones. On the personal side, obviously, I'm into hobby electronics. I have been a maker since I was about 15 years old, although back then I could barely figure out what unzipping a file meant. So we've come a long way. I'm into basketball. I like watching and playing basketball. And pretty much all water-related activities. I've been learning to surf this year, boogie boarding, heading out to the coast, and I've been working on this electric kayak on and off for about 1.5 years now. So why did I even start on this project? Well, Seattle has a huge water recreation and just outdoor culture in general. And so my hobby being so indoor focused, I wanted to try to marry the two and pick a project that would force me to get outside into nature. And also Seattle, it gets a bad rap, but it actually has pretty good weather for like 4-5 months out of the year. We won't talk about the other 4 or 5 months. I was also seeking a project where I could learn about AI and machine learning on the edge. And I wanted something different than just like downloading a computer vision Python library and just running with it. I wanted to figure out like, how do I train a model? How do I gather the training data? Those kind of details. And I wanted something being more hardware focused, I wanted some kind of obscure hardware based project that could truly benefit from AI, like in the real world, the physical world. And funny enough, Mario Party, the River Raft minigame on the Switch, is kind of what sent me in this direction. It was the first time I realized like I could use an accelerometer to measure like a paddle stroke and try to determine which direction the user's trying to turn. And I realized there's been this huge rise of e-bike tech and pedal assist, but there was nothing really like that for kayaking, and I'm not really sure why. Requirements that I set for myself was traveling at a walking pace, 3 to 4 miles per hour, 5 to like 6.5 kilometers per hour, 2-hour battery life. I wanted 2 different modes, a manual mode and a paddle assist mode. So manual mode would be like a constant motor speed, but you can toggle through different speed settings. Paddle assist, obviously, it's like the motor won't start until you start paddling and can try to figure out like which way you're trying to go. I've got an IMU, inertial measurement unit, on the paddle itself, which just measures like the yaw, pitch, roll, acceleration data, and the X, Y, and Z axis. I wanted a visual display, speed, battery life, mode, etc. And I wanted to spend less than $1,000. And most importantly, I wanted this thing to be hands-free. I wanted this to be as close to real kayaking as possible, not have like a controller in my hand or anything. The BOM, the motor and the motor controller, they're both from Flipski. So waterproof motor, a Vesk motor controller. It's an open source project. It's super good. I recommend it. Big battery, 24 volt, 20 amp hour, custom 3D printed fin, a bunch of Adafruit parts. I like Adafruit a lot. We got a Feather M0 microcontroller, a BNO85 IMU, a NeoPixel ring. Got these comms transceivers to talk between the paddle and the kayak side, and I use a Raspberry Pi. I'll go into more detail kind of about the system breakdown. Other than that, I had to build some custom boards, like this red board here I call it the Proto Power Hat. It's just a prototyping hat for the Raspberry Pi. It's got a built-in power button, cooling fan, a big prototyping area. I do sell this on my Tindy store if anyone's interested, but it just kind of cleans up messy breadboard projects. Kind of a system level overview. I have the kayak portion and the paddle controller half. So the kayak half is this Pelican case with a battery, motor controller, custom printed fin and everything. And the brains of the kayak half is the Raspberry Pi. So the Raspberry Pi eventually is going to read from this GPS module. It sends commands to the motor controller, and eventually is going to run the machine learning models to tell the motor controller how to drive the motor. The paddle controller is this guy here. It has the IMU inside, a NeoPixel display to display stuff to the user, and this user button here to set different speeds and modes and things. And there are an RF comms link with those NRF24 boards to stream data between the kayak Raspberry Pi and the paddle controller itself. So the paddle controller can send it IMU data, and the Raspberry Pi can send back motor feedback data. I don't have a lot of time to go into the details of the kayak side. I'll talk mostly about the paddle controller, but this part 1 video down here on my YouTube goes into way more detail here if you're interested in learning more. My initial testing started in a bathtub, just trying to get current draw versus RPM, tune the PID controllers and stuff, but it was too shallow and I kept sucking in water. So eventually I just had to get out there on the lake and see if the thing worked or not. And my first voyages, I just had my computer sitting in my lap like this right here, because I didn't have the paddle controller finished yet. So I had to drive everything from the computer. So I'm just out there in the middle of the lake with a computer in my lap. So on the first voyage, I got like PID tuning done, took temperature measurements, current draw, stuff like that. On my second range test, this is a map of Seattle here. So you've got the ocean or the sound here, Lake Union here, Space Needle down here. So there's a canal that runs between the sound and the lake, and that's where I did most of my testing. So it's like an 8-mile canal. So I think my range test, I'm estimating like 12, maybe 14 miles that I went, and I almost got stuck right in the middle, but it just turned out there was seaweed in the props, and I luckily got it running again. Otherwise, I would have had to paddle back to my car for like 4 miles. But I've also got a video on that full range test down here if you're interested on my YouTube as well. And here's a little sneak peek of what it looked like with me in the kayak with just a computer in my lap, turning along a few miles per hour. Everyone just giving me super weird looks, like thinking I'm working remote from a kayak or something. The paddle controller itself, my friend Jordan Godoy, he's a super talented designer, 3D modeler. I had him make the 3D printed mounts for me. So I gave him my inspiration of like a barbell clamp for like weightlifting that would slide onto the paddle and clamp down. And so he took that and kind of ran with it, and we went through a few iterations. Like first we kind of put all the electronics inside the clamp like this, but realized we'd have to make all these custom gaskets and it would be really hard to waterproof. So we moved to this like cylindrical design that we could easily waterproof just with like a couple O-rings, and that just a lot easier to work with. Like you can see down here is a cap with some O-rings. So after that, he started 3D printing stuff and just iterating on different designs and clamps and whatnot. And then eventually he got to this hook kind of clamp design that's like super strong. And we just had to put in some like squishy foam between the 3D prints and the paddle to give it more traction and squish and keep things from wiggling around. So he also designed this like slot for the electronics tray to slide in on a track into the cylinder, keep everything in place and secure, and this little battery slot to hide the battery and save some room. So some cool little features. The paddle controller electronics, like I said, I'm using the M0 microcontroller running FreeRTOS. It's got the NRF comms transceiver talking to the Raspberry Pi, an IMU tracking the position of the oar, and I made this custom board down here. I call it the Smart Click PCB, but it basically just lets me use a single button as a power switch and user input. So it's an ultra low power IC. When it gets the first button press, it wakes up, enables power to the rest of the circuits. Any button presses after that just act as like a simple GPIO input, and a long button press puts it back to sleep, turns off power to the whole system. So it's just a way for me to create a little low power device with a little more minimalistic UI, I guess. So the paddle controller firmware running FreeRTOS has a few different components. The RF components, there's a read and a write. So the paddle controller is reading battery voltage and motor speed from the Raspberry Pi, so it can indicate that to the user what speed and battery, how much battery we have left. It actually reads the kayak battery and the paddle controller battery and reports the lower of the two. And then it writes back to the Raspberry Pi speed commands, mode commands, and streams all of its IMU data. It reads button inputs from the user, and it can decipher between single and double clicks. So a double click toggles between manual mode and the paddle assist mode, and a single click when you're in manual mode toggles through like the 3 different speed settings. And then it also reports faults, so it shows you like a motor fault, comms fault, high current, temp, all that kind of stuff. And I've got a small little YouTube channel trying to get off the ground, so I've got some videos that describe like the paddle controller and how it works in more detail if you're interested in some more details. But I'll show you how the displays work. This is like the connecting animation, trying to connect to the Raspberry Pi on the kayak. This is the fault animation. This is if we get a connection, it runs through this startup sequence. And then you can see once we're connected, you can see the left side here is like battery status. So going from 0 to 100%, red to green. Then the speed status down here, I'm cycling through a few different speeds here. So that's low, medium, and high speeds get displayed out as well. And then the paddle controller itself, this is kind of it going together with the 3D printed enclosures. So it slides into the track there, and the button is built into the lid with the O-rings that waterproof everything. So once it gets turned on, single presses cycle through those speed settings. And then on the left side here, you can see like the battery right now is like 50%. The last demo I'll show you is the IMU data. So this graph up here is me taking the IMU data streamed from the paddle controller and plotting it in 3D space. So you can see it measures the yaw, pitch, and roll of the paddle, and I'm hoping that's enough information to train a machine learning model. It's a little bit laggy right now, so that's one thing I'm working on, is getting that sped up. And speaking of, that's the next steps and kind of improvements. Right now I have Jordan working on an upgraded 3D printed fin that actually has a servo inside of it so we can control the direction of the fin. Then I'm going to tune some machine learning models. I'm going to use Edge Impulse, and for now I'm just going to train with data, just taking in air, fake some data, and make sure I can get the control down. Once I've got that, I'm going to implement like the kayak GPS sensor, and that's what I'll use for the actual training data. So basically I'll correlate the paddle position versus GPS. So it'll say when I'm paddling this way, GPS turn left, and that's how like the machine learning models will get trained to know that it was a left turn. I also need to implement like active heading control, because right, my kayak's so cheap it just will literally go in circles instead of going straight. So I need some active control to keep it straight. Some other things I want to do: create a PCB for the anti-spark circuit, shrink all the paddle electronics, create some sort of dead man switch. If you drop the paddle, everything will turn off. All right, and that's where the project's at right now. If you're interested, my main social media is YouTube, and I'm actually pretty active on Instagram as well. I try to be wherever makers are, so I'm on Hackster, Hackaday, Instructables, and the project page is on GitHub. Everything's open source, so if anyone's interested in helping out or wants to work on anything, let me know. Could always use help, and just trying to make this thing as good as I can. So, thanks.
Thanks, Braden. That was amazing. We cannot wait to see the latest updates from Bare Naked Embedded on that kayak. Coming up next, we have a great project by Luigi Morelli. Him and his students developed a steamboat that could be controlled with Arduino or Raspberry Pi as part of their computer science final project. It is 3D printed. Check it out.
Hi, my name is Luigi Morelli. I am a teacher of the Biomedical Information courses at the ITS New Technologies for Life in Bergamo, Italy. I have been teaching computer science and electronics. The final exam of the electronics course consists of a project based on Arduino or similar microcontroller, and the test uses sensors and actuators driven by the Arduino board. I also run a science blog based on Raspberry Pi and Arduino information. The blog publishes news about boards and software, tutorials, code snippets, and so on. We decided to host in our blog the project of the electronic courses that better fit our needs, publish them both on the blog and on Hackster.io. The project we will deal about now is a scale model of a steamboat, one of those who plied the Mississippi in the 19th century, entirely functional and managed through Arduino. Let's go. The hardware component list is quite simple. We just used Arduino Uno, a receiver and transmitter for infrared, a motor, a cable, USB cable A to B to communicate with Arduino, RGB LED, an active buzzer for the siren, a power supply, a couple of resistors, an H-bridge for the motor, some DuPont connectors, a battery, and a battery clip. We also use some generic material like polystyrene, wire fabric, ice cream tub, a cardboard, and metal rod. Today we will get to know an ITS working group made up of Sara De Filippis, Silvia Magri, and Pietro Manenti in alphabetical order. As a final exam in the electronic course, the group presented another radio controller system, a wheeled boat. In addition to the classic electronic and software management problems, the project also involves some peculiar characteristics like buoyancy, maneuverability, resistance of the vehicle, waterproofing, which make interesting for publication. The initial project consists of the idealization of a boat that is capable of floating with the possibility of being able to coordinate and control its movement, the switching of an RGB LED, and the activation of an active buzzer like a siren, through the use of an infrared remote control. To carry out the project, we looked for an idea that could best reflect the desire to test oneself with, at the same time, choosing a project suitable for beginners. Modifications were therefore developed on the circuit and on the code, ultimately leaving room for aesthetic as well. A police siren parallelepiped was taken, which was cut into the shape of a boat with a knife. Subsequently, a series of holes were cut inside, into which the motor's batteries were inserted. The circuit was placed above the hull, covered by the ice cream tray to obtain greater circuit protection and better aesthetics. To fix the receiver input to position, to receive the signal, it was necessary to fix an iron rod to the hull, to which we attached a pink fabric sail using a spray can. The plastic tray was then fixed to the hull using wire. It was cut to obtain a satisfactory aesthetic result. We have carved the structure to show the LED at the top of the tray. Finally, the blades were printed in 3D in PLA using the Ender Chip 3D printer. Various difficulties were encountered in the implementation of the project. Search for an idea for the project to be implemented in line with initial knowledge. Many projects initially appeared interesting, but upon subsequent analysis, they turned out to be too complex for the level of knowledge gained by the group in the short space of the course. Programming the various cycles of the code. Although managing the individual sensor and actuators is trivial, adding more components to the project increases its complexity exponentially. Remote control range. The IR remote control, although equipped with a debouncing system for pressing the buttons, has a decidedly limited range of action. For this reason, the next version of the system involves the use of a steering system through web services connected via Wi-Fi to a cloud. Circuit composition, H-bridge with a pair of engines. We had to learn to manage the functions and activation times of pedal engine in water, study the power necessary to make the vessel move and curve without causing hydrofoil effects. 3D printing and printing time. Printing times for the blades were always higher than expected, both due to their complexity and to the waiting queue. Furthermore, we had to test different shovel models for different curvature, which would allow advancement without affecting too much the power required. Physical assembly of the boat's cable management. Contrary to the usual projects, the boat had to function in water. We therefore had to provide a waterproofing and protection system for the electrical circuits. Future extensions. For version 2.0 of the project, it was decided to improve the skeleton of the boat by making it more waterproof, faster and lighter, by installing more powerful engines and even more efficient blades. Furthermore, it was decided to make it an amphibious vehicle, installing blades with different shapes and wheels to reduce friction with the ground. Let's have a look at the code. As you can see, we only need the iRemote module. We define the pins of the engines 1 and 2, the RGB LED, the receiver and its pin on the remote control, the buzzer. We define the classical function to translate the signal of the infrared remote control, switching the results value and defining for each case a different action. We also take those values and write on the serial print to gather information. So we can turn the RGB LED on and off. We can turn on and off the buzzer, the siren. We can set the motor on to go steady, to turn left or right, inverting the movement of one of the blades. We can turn all the motors off to stop the boat, and also have a reverse that allows the boat to go in the other side. Then we set up the motors, the receiver, the LED, and the buzzer. The loop is quite simple. We have the loop that controls the decoding of the receiver of infrared, and if the flags set up on the translation are on, it performs a different action, like getting the lights, emitting the sound, having a bitonal siren, and the movement of the motors is worked directly in the function. So the code is quite simple. Final thoughts. Considering that the group had no previous knowledge of electronics and Arduino, and had just finished the Harvard CS50 course, Introduction to Computer Science, the results were pleasantly positive. The boys and girls learned to work in groups, dividing tasks and responsibilities, organizing the work into parallelizable modules, and carrying out in-depth quality assurance work before the delivery of the prototype. The choice of reusable materials shows attention toward green making, and the organization enabled them to deliver the finished and functioning prototype within the required deadline. Not only increased capabilities in terms of software and electronics, therefore, but also a whole series of skills that will come in handy once they enter the world of work.
Wow. Thank you so much, Louise, for sharing about your Arduino remote controlled steamboat. We cannot wait to see the latest updates. And now for our last impact spotlight of the day. This is going to be our Ross Ranger Mini radar and depth enabled AMR by Team Garud, a group of college students who have done something amazing. Please check it out.
We are Team Garud from the University School of Automation and Robotics at GGS IPO, New Delhi, India. And we are proud to present our Ross Ranger Mini project, an advanced autonomous mobile robo, also known as AMR. Before we dive into the technical specifications, we'd like you to meet the minds behind the machine. Our team consists of 5 members, each with their own technical specialty. We have Harshit, Vishal, Parth, Harneev, and Shlok, the group who put in an all-out effort in building this project. In this team, Harshit led the mechanical design, Vishal engineered the embedded systems and wireless connectivity, Parth developed the ROS software and SLAM algorithms, Harneev integrated all the hardware and sensors, and Shlok made the mobile app for remote operation. We hope you enjoy our video and learn something new today.
Autonomous mobile robots represent a paradigm shift in intelligent automation. Fundamentally different from traditional guided vehicles, these sophisticated systems navigate dynamically, using advanced sensors and artificial intelligence, adapting to their environment in real time. AMRs are transforming industries at an unprecedented scale, revolutionizing warehouse operations, optimizing healthcare logistics, and advancing agricultural monitoring systems. Unlike conventional automation, they think, learn, and make decisions independently. The global AMR market, valued at around $21.5 billion, is experiencing remarkable 23.7% annual growth, reflecting their critical role in Industry 4.0. From manufacturing efficiency to autonomous deliveries, AMRs are not just the future of robotics, they are reshaping how we approach intelligent automation today.
To get started with the particle photon 2, the first step is to register on the particle website. Once registered, you can check whether your device is connected through particle console like we see here. In our case, the device appeared right away, confirming successful connection. For development, I install Visual Studio Code and set up the particle CLI, which allows sending commands directly through the terminal. While working with the Photon 2, it's also important to understand its RGB LED indicators, as they reflect various modes like setup, connection, and error status. There are two main options for programming the Photon, using VS Code or the Particle Web IDE. Although I initially tried VS Code, I encountered a few issues, so I switched to the Web IDE, which offer a simpler and more intuitive interface. One key advantage is that it's already linked to the particle cloud, so there is no need to write an additional code for Wi-Fi or cloud connection. I just wrote the firmware, selected the device, and flashed it directly to the Photon 2.
In our project, we used MIT App Inventor to create a simple mobile app that communicates directly with the Photon 2 via the particle cloud. This allows us to control the robot remotely over the internet using clean, touch-friendly controls. We started by visiting appinventor.mit.edu website, signed in with a Google account, and created a new project. The user interface was designed using drag and drop components, buttons labeled with forward, backward, left, right, and stop. In the block section, we programmed each button to send an HTTP post request to a particle cloud function hosted on our Photon 2. The format we used was like this. The post body contained the desired command and our access token like this. For each button, a different argument value was used, such as forward, backward, left, right, and stop. These arguments were interpreted by a firmware running on the Photon 2 to control motor movement. To retrieve the device ID, just log into the particle console, select the device, and copy it. For the access token, we used these. Along with this, we also integrated a camera module with the robot. This camera captures live visual data from the robot's environment, which we used as a video feed input in our raw simulation. This allowed us to visually validate the robot's behavior and navigation path in a real time during testing and development. Finally, we tested the app using MIT AI2 Companion to live deploy the interface onto an Android phone. With this complete setup, we built a cloud connected AMR that not only receives mobile command but also stream visual input for use in simulation and AI tasks.
One of the core components of our AMR project is Visual SLAM, and for this we have been using Orb SLAM 3, one of the most advanced and versatile SLAM algorithms available today. SLAM, or simultaneous localization and mapping, allows a robot to build a map of an unknown environment while tracking its own position in real time. Unlike traditional SLAM systems that depend heavily on expensive lidars or depth sensors, Orb SLAM 3 is purely vision based. It works with monocular, stereo, or RGB cameras, making it highly cost effective, especially for budget sensitive applications like ours. Now, here's why Orb SLAM 3 is truly special and a perfect match for our use case. First, it supports multi-map tracking and loop closing. This means it can seamlessly detect when the rover revisits a previously seen location and adjusts the map accordingly, reducing drift and improving accuracy over time. Secondly, it offers full support for real-time localization even in large or dynamic environments. Whether the robo is moving fast or operating in a cluttered space, Orb SLAM 3 remains stable. Third, and this is a game changer, Orb SLAM 3 is the first open source SLAM system to unify visual inertial, and multi-map capabilities in one framework. This gives us a lot of flexibility as we scale or modify the project. We are not locked into one type of sensor or dataset. In our simulation, Orb SLAM 3 is running on synthetic camera feeds and successfully tracking the robo's motion across rooms, generating sparse 3D maps in real time. This helps us verify that even without a lidar, we can achieve precise mapping using only a camera and smart algorithms. By choosing OrbSlam 3, we are cutting hardware costs without compromising on accuracy, and we're laying the foundation for autonomous operations in complex environments. In future iterations, we can even extend the system to support visual inertial fusion or multi-robo mapping, all within the same framework. So for now, OrbSlam 3 is powering a robo's eyes, giving it the ability to perceive, map, and move confidently even in GPS denied or unknown spaces.
The future of robotics is arriving faster than ever imagined. Picture robots that learn and share knowledge with each other, creating an interconnected network of intelligent machines. Our Ross Ranger Mini will evolve to recognize objects and people, making decisions that seem almost human like. Imagine multiple robots working together like a perfectly coordinated team, sharing maps and coordinating tasks without any human intervention. These robots will process information instantly right where they are, making split second decisions for the better performance. With high speed internet connections, they'll tap into cloud based intelligence, becoming smarter every day. The robotics industry is exploding, growing from $71 billion to $150 billion by 2030. Soon, these intelligent machines will help in rescue operations, monitor our environment, assist in farming, and become a part of smart cities. We're not just building robots, we're creating the foundation for a world where intelligent machines work alongside humans, making life safer, more efficient, and remarkably more connected than ever before.
For the conclusion, our Ross Ranger Mini represents the vision of accessible and intelligent automation. By combining the cutting-edge technologies like the particle photon to intuitive mobile interfaces through MIT App Inventor and robust raw simulation environments. We have created a scalable platform for autonomous operations. This project demonstrates how emerging technologies can be integrated thoughtfully, which can lead to solve real-world challenges in industrial, agricultural, and educational sectors as we continue to innovate. The Ross Ranger Mini stands as the proof that the future of robotics is not just autonomous, but intelligently connected and remarkably accessible.
Great job, team, on the Ross Ranger Mini. I hope you guys have all enjoyed our July Impact Spotlight by Hackster.io. I would like to personally thank them for inviting me to MC this great event and to encourage all of you to subscribe to receive Impact Spotlights. Our next Impact Spotlight is happening in August. Make sure you're there on Thursday, August 28th, featuring projects all about connectivity technology. Make sure you come back again and stay STEMtastic.